approximation schemes for stabbing rectilinear polygons. So he said that he's okay with asking questions in the middle of the talk, but we'll also have 5 minutes at the end when we'll have hopefully a lively Q&A, and then also you can ask your questions. So over to you, Aditya.
Thank you. I hope I'm audible. Can someone give me a thumbs up? Yeah. All right. Right. So as just mentioned, my name is Aditya. I'm a PhD student at IIT Bangalore. And today I'm going to talk about approximation schemes for stabbing rectilinear polygons. This is joint work with my advisor, Arindam Khan, and with Tobias Whitman and Cindy from TU Munich. So hopefully we can at least take over the problem list from the talk. So feel free to ask questions during the talk. Right. This should, yeah. So let me start by explaining what the title itself means. It was a bunch of big words, which make sense to most of you, but there may be a few whom it doesn't. So when you're dealing with NP-hard problems, you cannot hope to solve the problem exactly and fast at the same time. So these days, most of us are dealing with NP-hard problems, so we have to give in one of these two things or sometimes both. So one thing you can do is you can give up on the fast part of it. So instead of going for an n to the constant, you might settle for an n to the polylog, which is called quasi-polynomial time, or you might settle for n to the n, which is exponential, and so on and so forth. And that's the n part of it. The other thing that you can do is you can approximate. You can give up on the exact part of your solution, and you can settle for what is called approximations. So what is an approximation? So I reached today morning, I have to get from the hostel to the venue. I don't know the route. Let's say the shortest path is 1 kilometer. I just want to get here somehow. I'm fine as long as, let's say, I can find some route that's 2 kilometers. So I would call this a true approximation. As long as my answer is not too far from the optimum, it's as long as it's an alpha factor away from the optimum, I call it an alpha factor approximation. And similarly, the title said approximation schemes. So what I'm going to talk about next is an approximation scheme. In that, so 2 is fine, but maybe you're not happy with a 2 or a 10. You want a better approximation. So let's say you give me any epsilon, as small an epsilon as you want, and I can spit out a 1 plus epsilon factor approximation that runs in polynomial time. Then we call that a PITAS, and that PITAS stands for polynomial time approximation scheme. The caveat here is that the runtime might depend on the exponent is a constant. As long as the epsilon you give me is a constant, the exponent is going to be a function of that epsilon. The smaller the epsilon, the runtime will go up. Similar to what this PITAS is, there is a QPITAS, which instead of polynomial time, that is for a quasi-polynomial time algorithm, which would be an n to the polylog runtime. All right, and just one more notion, that is that of ATX hardness, that if this class of problems, which if they are ATX hard, you cannot hope to get a PITAS for this problem. All right, then now onto the full word in the title, that is stabbing. So I give you a rectangle, and I call this rectangle to be stabbed if you draw a segment that crosses through it. In that if it hits both opposite sides of the rectangle, then I call the rectangle to be stabbed. Generally, we are dealing with axis-aligned rectangles and axis-aligned segments. So in this figure, as we can see, the green segments do stab the rectangle and the red ones don't. Okay, now the rectangle stabbed problem. I'm going to give you a set of n rectangles. And what I want you to do is I want you to stab all of the rectangles. What I want you to optimize is the total length of segments that you use to stab all the rectangles. I repeat again, it's the total length and not the number of segments. Both have different problems and they have different kind of solutions. Right, so here you can see a bunch of rectangles. And the blue segments that you see now end up, if you squint closely enough, you will realize that all the rectangles do get stabbed. And it also happens to be the optimal stabbing solution. So this is what the solution to a rectangle stabbing instance will look like. But the title said rectangular polygons. And what I'm given now is rectangles. So what is a rectangular polygon? This thing, as long as all the terms in my polygon are right angles, I call the polygon to be rectilinear. For the purpose of this talk, I'm going to be looking at a particular type of rectilinear polygon that I call a K shape, and hopefully that will be clear why it's okay to look at just these things. What is a K shape? It's a stack of K rectangles with the one property that conjugated rectangles either are complete subsets of the one below or complete supersets. So in that you don't have like a staircase structure in your K shape.
Definition of stabbing?
Yeah. Stabbing is I give you a rectangle. I call the rectangle to be stabbed. If you can, if you draw a segment that completely passes through the rectangle. So the green one is good, the red ones are not. Yeah.
So how does the definition extend to K shape? Like, do we want every?
I'm getting there. I'm getting there. I'm getting there. Yeah, right now I'm looking only at horizontal stabbing. Vertical is also studied. We'll get there too. K shape, I call a K shape to be stabbed if one of its constant rectangle is stabbed. That's it. Yeah, just one. All right, so why study stabbing? Apparently, it can be viewed as a resource allocation problem where, say, a request looks like a band of frequency band. So any of these frequencies are fine, but the time duration that the request wants frequency band to be allocated is fixed. We can allocate any of the following bands to serve that request. So on the frequency time plane, your problem will look like the rectangle stabbing problem, and the rectangles that do get assigned to server request will look like segments. You want to minimize the channels that are assigned, and hence this rectangle stabbing problem. This also happens to show up in some circuit design problems. There is a problem called the generalized minimum Manhattan network, GMMN. Generalized minimum Manhattan network problem, in that you are given a few pairs of terminals, and what you want to do is you want to find a minimum rectilinear network in that you're only allowed to draw access parallel lines to connect all of these terminals. Some circuit design problems get reduced to GMMN, and this to solve this, one of the approaches was to reduce this problem further to the horizontal rectangle side problem. And by giving better algorithms for this, we actually do slightly improve the known approximations for this problem. But that was for rectangle stabbing, like K shapes. I mean, of course, it covers a more general class of objects. What you see on board are tetrominos, the shapes that are used in the game of Tetris. One of these is not a K shape. This one, because it sort of has a staircase-like structure, these get covered. So hopefully this problem helps to generalize the class of scheduling that we could have done with rectangle stabbing. But another thing that sort of matters to me is that, so rectangle stabbing is a special case of set cover. Now, set cover is has a hardness of approximation of log n. You cannot do better than log n. But horizontal rectangle stabbing, you can do better than log n. So you can go where in this class of specialization for set cover does the actual hardness lie? And by looking at generalizations of the rectangle, we do find where that boundary is. All right, so what was known? So back in 2018, Timothy Chan and a bunch of his collaborators showed that the problem is NP-hard. They also give a constant approximation factor for algorithm for the problem. The constant is really bad. I tried looking at what it was, but I failed. Then 21, Ola Svensson and the group gave a Q beta for the problem. They also gave a nicer constant factor approximation. And then later, a subset of the current authors, that is me, Arindam, and Andy, gave a PTAS for this problem. and a 2 plus epsilon for the slightly general, the horizontal rectangle plus rectangle stabbing problem. Yeah, and that leaves what can I do further? And that's what this paper is about. So in our paper, we give a QP task for the rectilinear stabbing problem. Generally believe that if there is a QP task, there also is a P task. We don't know the P task yet. And as I was mentioning earlier, that this is a specialization of the set square problem. So we show that we give a QP task for a special case, like not just K-shapes, but even a specialization of them, in that when they satisfy the thing called the R-glass condition. But we also go ahead and show that if this R-glass condition is not satisfied, then the problem is APX hard even for 3 shapes, that is stack of 3 rectangles. Okay, we are making some progress. We already found something that's a bit harder than set cover, than just rectangle stabbing. And then further, without too much extra work, we can also show that the K stabbing problem, not 3 but K, is set cover hard in that we cannot do better than log n approximation. So we'll accept. Then we also show for further some special cases, we can show a p-task or a K approximation for some more special case of rectilinear stabbing. All right, so what is this? Yeah.
So I think I understand the K-shaped problem very clearly, because why can't we simply stab the smallest rectangle and why is that not possible?
Great question. I should have put a counter example on the slides. Well, it was not a single K-shape. So, I mean, same for rectangles, you can technically just stab all rectangles. Okay, that's not exactly the same. But yeah, because of overlap between different K-shapes, like stabbing the smallest one will not work. I can maybe show you an example offline. But yeah, that does not work. But yeah, good question. Fair enough. It's just a rectangle. But for that case, we do have p-task already. There are counter examples. Let's take that one offline. Is everyone on board with the problem at least? We can follow the problem. What the results are. All right. Then I will move ahead. Is this hourglass condition that I mentioned, for which you can give a QP task? I mean, basically the shape roughly looks like an hourglass in that there is one decreasing sequence of rectangles and then an increasing sequence of rectangles. It cannot be increasing and then decreasing. There's like a minimum rectangle in the center. So the first one you see is an hourglass, but the second and third are also hourglasses because they only have the increasing or only have the decreasing. These things are not hourglasses because there is no sort of narrow nick at the center. Yeah, the second one is not a K-shape. Good catch. The first one is a K-shape. The second is not a K-shape. Yeah. Right. All right. So if everyone's on board, I will go ahead and show you a reduction as to why when we are dealing with 3 shapes which don't satisfy the hourglass condition, as you can see, sort of goes wide and comes back. To look at that kind of shapes, with just 3 shapes, I will try to show you that this is APX hard. So the reduction I'm going to use is going to be from vertex cover. From the vertex cover problem, you're given a graph. The set of edges, you want to pick a subset of vertices so that each edge in the graph has at least one of its vertices in the vertex cover. So I'm going to give a reduction from that instance of vertex cover. I'm going to construct an instance of 3 stabbing, and the object equivalence is going to be an approximation preserving reduction. The object equivalences are going to be for each vertex in the graph. I'm going to create a unique square that you see here on the left, these green squares that you see, and for every edge in the graph, I'm going to construct a 3 shape that so because there is a vertex corresponding, it's a square corresponding to each vertex, you can now construct an edge that sort of corresponds to the two squares that have been constructed for the K-shape instance, T-shape instance. And so with how do I construct this three shape? It is just the square, the two corresponding squares, and a wide rectangle that has width n plus 1, where n is the number of vertices in my vertex cover instance. So why do I do this? This is because if you want to stab any of these K-shapes, it never makes sense to stab the K-shape along the y rectangle. The width of a single y rectangle is n plus 1, while there are only n of these unit squares. So I can always have a solution of total length n that stabs all of these K-shapes. So I'm never going to stab a K-shape along the y rectangle. And this is where I'm using the fact that it is not, in some sense, that it is not hourglass. And yeah, and now any solution, any optimal solution to the stabbing instance is going to correspond to the optimal solution of the vertex cover instance, because by stabbing, if you are going to only stab a K-shape along the unit square, you can translate that solution on a vertex cover where the stab unit square is a vertex that is picked, and vice versa. So yeah, just the two edges that are drawn here, if you look at the graph, I mean, there can be a lot more edges, there can be a lot more K-shapes here, but if you look at it, V1 and V2, the vertices correspond to unit squares. The edge between V1 and V2 is this K-shape with a wide rectangle in between. All right, so the vertex cover is APX hard, and hence, if I can solve the K-stabbing instance, I can also solve the vertex cover instance, and hence K-stabbing is also APX hard. I don't think I have time to go over the QP task, so I will. Do I have 3 minutes more, or can I open it to questions? 8 minutes? Okay. Then give you a quick overview of what the QP test, that was the low bound. What does the upper bound look like? Right. So was there a question? Right. Yeah, this is what an instance of K-stabbing could look like. So the first thing that we do is I'm going to divide the instance into this a very broad overview of the algorithm. I'm pushing a lot of details under the rug. If you want to go into the details, you can catch me offline and we're happy to talk about it. Yeah. So first thing we do is we divide our instance into narrow vertical strips of this particular width. And I'm going to do a random offset for reasons that will remain mysterious during this talk. Then you see that every K-shape that gets intersected by the vertical grid line that I have drawn is something I'm going to handle separately. I have good algorithms for solving instances that say lie along a line or some such stuff. So those are going to be handled separately, and I'm going to get good approximations for those. For the remaining stuff, I'm going to now further partition the vertical strip into horizontal slabs, where I can sort of start with a sort of like a sweep line that goes bottom to up, and I can compute an approximation, a bad approximation, but an approximation still for the size of the solution. And as soon as the size of the solution sort of goes above some threshold, I'm going to draw a horizontal line to further divide the instance. This is to ensure that the solution inside every slab I have is sort of small enough that I can guess the segments which are very long. Once I can guess the long segments, I know that if there is, by guessing, I just mean you can enumerate all of them, and you can check if any of these are correct by actually going through all of them. So for the correct instance, for the correct guess, you know that any rectangle that's left that is really wide. There is no way that this is going to be stabbed by by a segment of that length. So I can just ignore those. And this is where crucially we use the fact that this is an R glass, because once I remove the wide rectangle, I still want my shape to be connected. So because it's sort of an hourglass, the widest shapes are going to lie at the extremities. And even when I remove them, I still have a connected shape remaining with me. Once I do that, I just recurse. And this magically, this works and gives me a QPTAS. So that was the rough overview of my QPTAS. And I leave you with two open problems. One is, what is the QPTAS for this? If QPTAS exists, can you find it? And the other thing is, even for rectangles, give a PTAS for just horizontal stabbing. If you're allowed to use vertical segments too, you don't know what the how good the approximation ratio can be. Can you find a PTAS for that? So yeah, I leave you with that. Thank you.
Do we have enough time for questions?
What are the questions that?
The brownie one,
Yeah.
they're coming. First, other questions and then
So, are there any TCP kind of hardness of approximation results here?
I am not aware of this.
Okay.
Sorry. Yeah.
Do you know something about general convex bodies?
You will have to define what stabbing means for convex bodies. So even here, this is very specific where the segments and the shapes are axis aligned. Now, if I allow you to have non-axis aligned even segments, you can sort of just stab things at a point. That's what the conceptual thing. Again, the convex body is whatever it means to stab a shape is not clear. You can define it, you can solve it, but it's not been done yet.
Okay, I see. Makes sense. Yeah. So this is actually two questions. What about general polygons? Okay, I think that's what you already answered.
Yeah.
What about high dimensions? Does that question make
High
sense?
dimensions. Again, what do you mean by stabbing? Do you want a segment? Do you want a plane? It's not been defined yet, is all I'm saying. And it's not a very natural generalization. You have to define it, and for whatever generalization you go for, maybe you can solve it. But there's something that has shown up previously in the literature, hence we looked at this, but application wise, it's not.
So in this case, can you because the rectangles whose width is space between the borders, right? Yeah. So usually cases of overlapping in this multiples can overlap in this case.
So there will be overlap, and that's the point sort of the stabbing problem itself. If there is no overlap between shapes, the only thing you can do is stab every shape individually. And in that case, for K shapes, the best thing to do will be stab the narrowest part of it. You will be overlap. But the thing is, whatever the overlap is, you are never going to stab shape along the widest rectangle, because the length, the width of that is n plus 1. It's a simple solution of length n. That answer the question?
Or something like this.
Online has not been studied, but I would imagine that would be the K shapes are given up front.
Okay.
Sorry, no.
This line is
Some shapes come online and
no.
segments one by one. That would be the only setting.
no question. Okay, let's hang the speaker and then I'll. So based on what I wanted to ask, I think the point of the brownie question is that everybody can actually have a brownie. So let's. So in one of the earlier slides, he had a nice slide describing the various kinds of approximation algorithms that have been studied. There was constant factor, QPTAS, and PTAS. In particular, this question about there was a PTAS for horizontal rectangle stabbing. Do you remember what is the best known result for general rectangle stabbing? Especially since people were asking about general polygon stabbing and so on.
2 plus.
So he raised his hand.
Okay, sir.
You get credit, but he should probably get the brownie.
Yeah.
Okay, he didn't follow protocol. Okay. So, all right, yeah, was this thing. Okay. All right, so the next speaker can. Ready? Okay. So it's wonderful. I just want to say that these are all students, PhD students whom I have met years before, and they're doing wonderful work. So that gives me great pleasure. So this is wonderful. So this is the last talk in this session. So it's about parallel complexity of geometric bipartite matching. So yeah, you can start.
Okay, now audible. Okay, good morning. I'm Sarfraz Iqbal. I'm today going to talk on my recent work on parallel complexity of geometrical bipartite matching. And this is joint work with Professor Rohit Gujar and Professor Sujay Bhore. Okay, so let's start with what is matching problem. So it's very general problem and it's defined on graph. So we have set of vertices and a set of edges. We wanted to find a subset of edges such that the vertices, the part of the subset will at most part of one edge only. So the colored edges in this graph is matching. But we are interested in finding perfect matching. The matching that is expanding the whole graph. So each vertices must be part of the matching and the exact one edge of the matching. But we are looking into the graph. And in the right graph, we have set of vertices that is divided into two parts, vertices. So, and the edges between vertices. And to find the perfect matching in the bipartite graph, it's in bipartite matching. There are multiple applications of bipartite matching, like doing the percent matching, the applicant and all. There are multiple applications of bipartite matching. It's well defined. So there are weighted version of same problem, same matching problem, where we have a set of weight on the edges, and we wanted to find with perfect matching, where the perfect matching have the weights minimum weight over the perfect matching in the graph. So in this case, this is the perfect matching. We call it minimum. So there are known results for finding the perfect matching in the general graph. And Edmund solved this problem in 1965 only. This is the polynomial algorithms for finding a perfect matching. So we are talking about this. It's already solved in 1965. The is open for parallel complexity. Still, we don't have any efficient algorithms for finding the perfect matching in parallel complexity. But there are some known results even for parallel complexity. And but before going into parallel complexity, I want to talk about what is efficient class in parallel complexity. Like the class called NC in just like P in normal setting, we believe NC class is efficient class in parallel complexity. And this is kind of we have a processor. And we are now working with time to solve the problem. If we can solve this problem in this resource, we call the problem is in NC class. So we believe NC class is efficient in parallel complexity. In 1979 only, Loas gave an algorithms that will work in NC time, but that algorithm is randomized. So we have NC algorithms, but it is randomized. So the main question we is can we remove this randomness and we have efficient algorithms in without randomness? After many decades, in 2016 only, Fernald Guzer and Durov come up with a they remove the randomness from the problem from the algorithm. But this is only work for the bipartite graph. And the depth of the graph is not login, but quasi-polynomial depth. So the problem like it's quasi-NC, but still it's not efficient. In 2017, Sevens and Chomsky gave an algorithms that they extend that algorithms and they gave an algorithm that will work for any given graph, but they still it's quasi-NC. So we are still looking into NC algorithms. Lately, like recently, Amari and Nazirani gave in 2020 algorithms that is NC, but it will work on the general linear graph. So motivated by this result, we started looking into some special piece of graph where we can say like for which special class we can have NC algorithm. So we started looking some special class graph and we want like geometrical with data matching like that is defined in geometrical matching is in NC. So what is geometrical data matching? Where the vertices of the graph or bipartite graph is given as a coordinate terms of R2 dimension. So these are the points and the points are like vertices are given as coordinate points. And the edges between them is a kind of a LP norm. So instead of this talk, I will talk about the LP norm, but the results are like valid for any LP norm, like P is greater than 1. So finding the minimum with perfect matching in this graph is geometrical data, like geometrical minimum with perfect matching, GWBPM. We can think of the application of this geometrical data matching as like we have robots and some payloads. We wanted to match the robots with the payloads. So the distance between them is kind of age weights of the graph. As like we have general LP norms results, but in this talk I will talk only about the L2 norm. So when we started solving the GWPM, the like natural way to go to design an NC algorithms for the geometrical bipartite matching is those NDV algorithms. And NDV algorithms require a polynomial bounded age weights. And in the geometrical bipartite matching, age weights are root square roots. So it's like it can be a Russell number. And we don't know exactly like it is not we can we compare the two irrational number or something like can we have add the something like exact irrational number. So like when we are thinking about the geometrical pattern matching, we have to think about the complexity of like the complexity of the weights. And it is we are thinking about the big complexity in this problem. Like in the general setting, it is P or NP because like in all that main algorithms, are like kind of unit cost, but it's not clear when we are exactly when it is reversal number, it's not clear how it's unit weight. So the natural way, like we come up an approximate version of this problem, where we wanted to find a perfect matching that is delta far from the perfect matching, and that we call like delta GWPM. So for further results, we talk about the delta GWPM. Okay, so what are our results are like we have two results in like two front. One where we first prove that if you have a data matching, geometrical data matching, it can possible like there is a perfect matching and some other matching, and the gap between them is exponentially small. So we solve delta GWPM for delta like polynomial is very small, we would solve the exact problem. So the first result says that if you find any like exponentially small, then if even like for exponentially small delta, so will be like the result will not solve. And the second result is like with the polynomial, like when the polynomial relative error, will can be solved in like NC time. So I will go one by one to both of the result. The first result for lower bound, what we did like we constructed a geometrical bipartite matching, and we saw like there can be two perfect matching where the difference between these two perfect matching we can be like really small. It's exactly 1 by n-1 perfect factorial. And then, but this two matching will not be like perfect matching. So, but our goal is to solve like one is minimum perfect matching and other is other can be imperfect matching and the difference is small. So what we do like we modify the graph and like in some some the like we modified the graph and the perfect matching that is construction one will be there. The difference of and one of them is one of the perfect matching that from construction one will be the perfect matching. So then these two construction will say like that we have a perfect matching and some other matching and the gap is very small. So what is construction one? So, for construction one, we consider the n vertices u1 to un minus 1 on the in terms of 0, 0, 0, 1, 0, 2 like this. So these vertices are at kind of piles on y axis 0, 1. And then the right side vertices are qn, q2n, q3n, and qn square. So on there is like q is integral 6. So like the other vertices, green vertices are far from red vertices, and they are 6 distance, and the different and the gap between the green vertices is like each vertex of n. So and matching between like this kind of construction we have, and that is the going for the first construction, like the all matching in this construction one, the geometrical matching in the construction one, all matching have unique weight. So this is first claim we have, and why this is true. I'm not going to prove it like formally, but like overview, because like age weights are square roots, and a lot of the if we able to do like these age weights are independent and rationals, then this subset of that will be sum is equal. So any subset will take and unique sum. And the matching is the set of this age weight. So if you have a matching, then that matching will not have equal weights. How do we prove this independence? And like what we do, like this is how the each age weights is pairwise independent, and this is sufficient to say like when this is a square root of integer, it's sufficient to say like pairwise independent is like will say like linear independent, it's all linearly independent. And for details, it's not here. We can talk later if you want any detail of this. So the next claim on this for construction one is like that like in this construction there is two perfect matching where the gap is very small, like 1 by 1 minus factorial. And why this is true? Because like in construction one we have complete gap because it's sorry, it's a like geometrical matching where each vertex is matched with everyone. So we have in factorial perfect matching, and from claim one like each perfect matching having like different unique weight. And these weights are range between integer 7 to integer 7 plus n. Why? Because like if you think about the meaning, we can go on the construction one. The minimum age in between these two set is must be q. So q is into 6. So each age must be q by 6 into 6. And there can be there must be like n ages in this in any perfect matching. So the minimum weight of the any perfect matching is 7. And similarly, like if you will see like highest age weight will be into 6 plus 1. So and then if there is like n ages, so the maximum weight of any perfect matching will be n to the 7 plus n. So range is n, and we have n factorial matching. So the Pujan principle, it's like there must be two matching, and that difference is very small. Then what we did like for construction two, we like took the two matching that is very close to each other. Let's assume like one is M1 and M2, and different like the smallest one of M1 and M2 is M1. And then what we did for like if you take the union of two perfect matching, then it is a set of vertex disjoint cycles and the ages. So we common edges, but we focus on the cycles. And what we did, we like arrange the pages in sequence E1 to E12, where we arrange the cycles and arbitrary order. And each page is like E1 to EL. What we did, like we take any cycle and we take the age that is from M1, and the Y coordinate is like minimum. So we took that age first, and then we go on the cycles and because these cycles have alternate ages from M1 M2. So the ages is like E1 is from if M1, then M2 is E2 is from M2, and so on. So and then what we did, like we unroll the cycles and these ages, and we make some new construction that we will see in this next slide. Okay, in this slide we can see like the okay. I think okay, this is like the cycle. In this graph, I'm just talking about the one cycle. So this is cycle. So what we did, like we took the E1 and put it with the like this is the second construction where we put the E2 same length, same distance, but and then when we talking about the second age E2, we just we put the same angle of the age, the direction is opposite. So like further and kind of unrolling the cycle. So we unroll the cycle and we like these are the formal definition of the construction. And then what we did, we added three extra vertices, that is S0, S1, and S2, like on the corner of on the lower part of the vertices. And the coordinate of these vertices are 0 and 2 minus 2 LQ, LQ and 2 LQ. And the last S3, S2 is like 2 LQ minus 2 LQ. So the distance, if you see like the distance from S0 and the construction is 2 LQ. And similarly, like the distance from S0 to S2 is also 2 LQ. So if you go like if you observe this closely, you will see like there is a perfect matching in new construction M1 dash and M2 dash that is corresponding to M1 dash and M2 dash, where all ages from M1, like M1 dash have all ages from M1, and there's two extra age that we create three vertices. From that we have two extra age, the P2LQ and S2, and from S0 to S1. And similarly, M2 does have same ages for as M2 and two extra ages. This all ages like E1 and E2 are having same length because we didn't change the length, but this angle of the edges. So the age length of all E1 to E2 is same. Then and then if you will see the weight of M1 dash is equal to the weight of M1 plus 3LQ, and 3LQ is coming from the two extra A's that added in the M1 dash. And similarly, weight of M2 dash is equal to weight of M2 plus 3LQ. So the difference between M1 and M2, sorry, M1 and dash and M2 dash is equal like difference of M1 and M2. So newly constructed graph, the difference of M1 dash and M2 dash is same as the difference between M1 and M2. That says like, and then we prove like because all other comes now, all other perfect matching that is not like E1 as the ages. We will be perfect matching constructed graph. And there are some different, we can do like some perfect matching, but we think like the perfect matching in the newly constructed graph is must be M1 dash. And then it's like directly from the construction one, like the difference between M1 dash and M2 dash is same as M1 M2. So it's 1 minus n minus 1 factorial. So this construction one and construction two together, it's say like we have some like we can have geometrical bipartite matching where the two matching is very close to each other. So finding the delta GW2 for any polynomial delta will not work. So then the second result, for the second result, we say like delta probability have an NC algorithm, and this result is also goes by MVV algorithm. So if you use the classical MVV algorithms, that says like if you have a graph, and if you can design a weight such that the mean of perfect matching will be uniquely identified and kind of isolated, then we can find the mean of perfect matching in that graph in NC time. So we use this result and we try to design a weight assignment that will isolate the mean of perfect matching. And in this regard, what we did, like we first observed that the union of mean of perfect matching in geometrical pattern matching will be a planar graph. Why this is true? Because I'm not going to prove this full result, but can solve like one example. If you have a a geometrical pattern matching and there are two matching M1 and M2, they are minimum with perfect matching, and they are like two edge from one edge from M1 and one edge from M2, and they are crossing each other, and they are from one cycle. Then you can construct a different cycle where the edges are like this. We just what we did like in the cycle in the part of C2 cycle, we alternate the edges and we add the two edges that is like a state like in place of crossing we add the state edges, and now in second construction like M1 dash and M2 will have sum is smaller than the M1 M2 in the first construction. So that means like we have we consider that the M1 M2 is perfect matching, but M1 M2 is smaller than that. That is not possible. This kind of construction we did, and we saw that there cannot be any matching that is crossing each other. So then it is a planar graph, and then we use Theory and Vinod have a result and like weight assignment that will work for planar graph. We added that weight assignment with the image weights as a distance, and then with some appropriate constant, and this will work for geometrical bipartite matching. And then it is the weight of this. Both of the edges are polynomially bounded, so we can say like it will work like MVV algorithm will work on that weight assignment, and this will give us a NC algorithm. That's all, and the open question is kind of we can think about non-bipartite geometrical bipartite matching, and then the most general question is like can we find NC algorithms for general graph? That's all.
Any questions?
In context of parallel algorithms and in the context of bipartite matching, can you give an idea of what are the basic computations that are being happening in parallel? Like, is it looking at the weights in adjacency metrics or?
Yeah, like we use MVV algorithm. So MVV algorithms is using weight of the assignment, and like exactly see. I'm not sure like what exactly MVV algorithm is doing, but we are using the MVV algorithms as black box.
Okay.
So you described the problem as on R2 space.
Yeah.
Will it change if you extend it to any three dimensions or further?
Yes, because like we don't know how we will prove the crossing in higher dimension.
So planarity is the
planarity.
Right now, in the end, you showed that a matching cannot. Okay, the matching that we have, that you showed that the matching cannot be non-planar. You can swap the matching edges, so that it becomes
matching, but like union of perfect matching.
Yes. Yeah. Okay. So, but does it also allow you to remove all the crossing edges?
Crossing edges.
Yes.
So like when the graph have crossing edges, but when you get the minimum with perfect matching, there can be multiple minimum perfect matching, and then the union of this will not have crossing. Because the crossing edges, we can, if you are having the crossing edge as matching edge, then we can construct some other, because the graph is complete graph. In geometrical arrays, we have complete graph. So there must be edge from the state edges is there. So you have to add that edge, that will give you the minimum bit. Then the crossing will not, it's not, the crossing will not goes in minimum or perfect matching.
No, that I follow, but I'm saying that since you're using this algorithm for planar graphs as a black box, so shouldn't the underlying graph be reduced to a planar graph first?
No.
Okay, I'll talk about
Okay.
this offline.
What was wrong with the L1 norm?
I think L1 norm is not kind of distance, but it's like a Hamiltonian, sorry, it's not Hamiltonian, it says, no, like x1 and x2. Then it's not like how we are doing, we are crossing over this. It can be like multiple edge and that section, and it's
So, Safras, yesterday there was a talk on this optical transport and these problems. So there was a talk on optical transport yesterday by Pankaj. And
I didn't follow what.
I'm saying, so Pankaj yesterday.
Okay.
So which is about finding distances between probability distributions. And you talk about open the geometric setting.
Okay.
Those problems similar.
Okay.
So it's what problem also studied on this parallel complexity domain.
I don't know exactly, sorry. I'm like, I didn't, I don't, I think I don't, I was not in that talk, so I don't know exactly.
Okay.
Sorry.
But you should, I mean, I think it's a very good question. You should study.
Any other questions? Okay, so I guess we can now ask the brownie question, which is what I think everybody's waiting for. Okay, so this talk was quite, he tried to give the sort of the proof and the contours of the proof. So I have a step, and Sarfraz, you can correct me. The first step involved showing by a nice beautiful argument that the difference in the weight of perfect matching with that of the next higher perfect matching is bounded. To remember what that bound was. Okay. Yes. And what is the step 2? After this?
Taking one of them, the minimal weight for
Yes, that's right. Okay, good. So at least people got the first 2 steps of the long proof. Okay, we'll just take down your names, okay, at the end of this. No, I thought the first one was too easy. So then, yes, of course, if Neil has enough brownies, she can give away more. And maybe you can wait in queue to get an extra if there are extra brownies, but that one goes to him. Okay. All right. An important announcement, the cell phone. Okay, okay. There was a missing cell phone for a little while, but I think that wraps up the session.